My name is David Kjerrumgaard. I'm a Apache Pulsar committer. That means in the Apache open source world, not only can I contribute code, but I can also approve patches from other people and get them merged into the code base. I'm also the author of Pulsar in Action, which is available for free download on the StreamNative website. If you go to our resources section, ebooks, it's there available for download. The entire book is available. I encourage you to access that wonderful free resource. I spent 18 months writing it. Hopefully you can get some more additional information out of that after the course. All right. Well, thank you, everyone. Welcome to this training session about understanding Pulsar functions. So let's talk about the course learning objectives. We'll start with a quick introduction to Pulsar functions, what they are, what they're all about, what they do. Then we'll get into writing Pulsar functions, how to write simple Pulsar functions. Next, we'll talk about, after you've written these functions, how to package and configure Pulsar functions for deployment. Then we'll talk about the deploying of the Pulsar functions themselves. And your different runtime options for deploying Pulsar functions, where they can run, whether function workers or Kubernetes pods, things like that. And last but not least, we'll talk about the upcoming FunctionMesh Kubernetes operator that helps you manage and make the deployment of multiple Pulsar functions a simpler and a much more easier process for function writers. So with that, so let's begin with introduction to Pulsar functions, what they are. With this, in this section, we'll describe what Pulsar functions are and their utility as a lightweight stream processing framework, understand the basic Pulsar functions architecture, and start with some code examples to begin writing Pulsar functions, or at least give you an outline of what the API looks like, so you get an idea of how you're going to start writing Pulsar functions. So what are Pulsar functions? Right, they were designed as a serverless computing framework that runs on top of Pulsar. You can think of them like AWS Lambdas or other functions as a service frameworks by your traditional cloud providers, in that you're not really tied to any infrastructure you have to spin up to run these individual pieces of code, but rather they'll run in a serverless manner. You just deploy these pieces of code to Pulsar, and Pulsar takes care of all the internal wiring to make sure that the messages arrive, that they have an execution environment to execute the code in, and if they produce an output message published to a topic, that's all handled for you automatically. What they do is take care of a lot of the boilerplate code that you would traditionally write if you use a traditional client API to set up the producers and the consumers, the creating of the client, object, and creating all the different configuration of what subscription types you're doing, what your acknowledgement type is, your message timeouts, all that different information is configurable, but that's handled for you automatically. You don't have to worry about that. You do it through configuration rather than code, which is always a nice pattern to use. And then they're a nice way to run individual units of code that respond to individual messages that arrive on one or more topics. You can have them subscribe to multiple topics, and we'll get into that in a little bit. So this is the basic programming model here. You'll see it in our documentation. It covers it here, where you can have a Pulsar function can explicitly listen to one or multiple topics. You can do this either by listing them explicitly as an array when you configure them, or you can use things like regex patterns to say, I want to listen to these individual input topics. And then when an individual message arrives on any of these topics, a Pulsar function is automatically executed, and the user's code takes that message as an input parameter, does some processing logic on it, and has the option to, if it wants to, produce the output to a secondary output topic, publish the results of that processing, or it could be a sync and do nothing. It could just do some manipulation of like a database or something internally in the code and not have to produce a topic. That's an optional, as indicated by the dotted line there, and also has access to a log topic as well. You can, record some information if you want to track the processing of your different messages, or if there's errors, exceptions occur within your Pulsar functions. You can publish them to a persistent log, and then you can monitor that log for error conditions and things like that as well, for alerting and auditing and things like that. So you have all these different availabilities there. And not shown here, but last but not least, is the ability to record a metric. So Pulsar functions have a way of recording individual metrics. You can define your own metrics that can be exposed through Prometheus for monitoring as well. You can do things like the number of messages handled by a function is one good use case, or number of exceptions, or whatever way you want to define your metrics. There's a simple API for doing that as well. So lots of good features available in a Pulsar function. So why do we develop Pulsar functions? So back around 2017, 2018, when I was working at another startup, StreamNative, we decided to come up with Pulsar functions because a lot of, up to that point, distributed processing of any Pulsar messages in a highly distributed way required setting up a whole another distributed processing framework or engine. Things like Apache Storm or Heron or Flink or something like that that were really, really heavyweight computing engines, complex engines in and of themselves, an additional burden to just do some simple processing. And people thought, well, there has to be a better way than having to stand up Flink just to do, content enrichment on a message as they come in, right? There was no other really methodology to do that. The other option was to write something like, thought about writing something like the K streams had, where we write our own, but that didn't seem like a good approach at that time either. So we really decided, hey, let's have Pulsar functions, make it a serverless framework, and so you can do simple execution on this data, right? 80% of the processing you're doing on this data for things like ETL data ingestion pipelines are very simple pieces of logic, and so we make something that has a lower barrier to entry. You don't have to learn another processing engine just to produce some logic on it. We've decided we're going to write what's called Pulsar functions, and that's designed to maximize developer productivity, right? If you know a simple programming language in Java, Python, or Go, and you can implement a single method, then you can get very productive very quickly with Pulsar functions. So it's a very low barrier entry to stream processing with Pulsar. And that's kind of the point here. They're designed to perform lightweight stream processing and excel at basic use cases that don't require these complex stream processing engines, right? So it's things like per message transformations, normalizations, cleanups, lookups, enriching with metadata, things like that. Simple aggregations can also be done. We support basic windowing functions. You can do sliding windows. You can do tumbling windows for computing averages or counts or other basic mathematical properties over a stream of data as well, where you can tolerate some duplicates so you don't have necessarily reprocessing could occur in these scenarios as well. And then you can start building them into chain sequences of transformations, right? So you could see, again, simple ETL pipelines can start to be constructed by having function 1 do this, and then function 2 do another thing, and function 3 do a third thing, and then the output finally be a normalized, cleaned up, metadata enriched piece of data from the original input topic, and have it all done using just a sequence of Pulsar functions. So obviously they're a great solution, but they're not the solution for everything. They fit certain use cases and they don't fit others. Other things are still reserved for these more complex stream processing engines like Flink or Spark or Storm or Heron, these other ones that we try to get away from, that handle more complex processing engines, things like joining or merging multiple streams together. Pulsar functions is not great for that, so don't use it for anything that needs to wait on things like that. Things like syncing up event time, for example. You're listening to 2 different topics with a Pulsar function. You're never guaranteed to get data that has the same timestamp. You could have late arriving data in one and not the other. And so making these assumptions is not, necessarily a good thing to do when you're processing the data in real time. Things like Flink can handle that for you. You're manipulating a cursor at a lower level, so the reader can go back and find data from stream A and stream B that occurred in the same time window, and then do processing on that, for example. All right. Again, you don't want to do a chain sequence of events with different partition keys, because the data is going to be distributed across different partitions. You're going to get the data at different times. And so again, that's not a very good use case, or any sort of complex stateful processing engine with strict ordering requirements and exactly once requirements. These are just capabilities Pulsar functions don't have. Exactly once or strict ordering guarantees. They're sort of very loose guarantees and with respect to ordering and exactly once semantics, processing semantics. So now that we've given some background information, let's start with basically understanding the difference between what we call native Pulsar functions and the Pulsar SDK functions. And there's also a new extended SDK that came out, I think, in the 2.10, which expands upon the original SDK Pulsar functions, adds some additional hook and initialization methods. We'll talk about that. And then we'll show some code examples to get you started with Pulsar functions and Python and Java and Go. All those different examples will be shown here. And there are some examples also in the notes. If we want to post those examples, there's some existing examples in the main Apache Pulsar project as well under Pulsar Functions. There's a Java examples as well. There you can get some more examples here, but these are some that I've shown here. So first, let's talk about what we call native functions. So when we first got started, we said, let's try not to have an SDK implementation. Let's see if we can support a language native interface for a simple, clean approach for Pulsar functions that don't require the overhead of a Pulsar SDK, some library dependencies like that. So we call these things native functions. They're only available in Java or Python. Go does not have this concept. So you basically can write code that does not depend on any Apache Pulsar libraries whatsoever. And they're very useful for very simple operations. So again, if you want to just make something very clean and simple, you can use what's called native functions. And in order to use a native function in Java, you have to extend this function method, or this interface definition actually that's defined in the Java util. The basic JDK library includes this interface definition. And it has a single, which defines a single method called apply. Here, again, it's strongly typed. You can take any type you want. In this case, we're taking a string and we're going to return a string. So we've implemented it here as a string and string. And you can see this assumes that, again, a Pulsar method has to be on that topic that you're subscribing to, must have a type of schema string. You get these messages that will be passed in automatically as the input parameter. And then you do simple operations on it, do whatever you want on this particular object, and then you're returning a string. And what this return does is automatically use the producer that's created internally inside the Pulsar function, and will publish it to the output topic. And that, assuming that output topic also has a schema type of string as well. Otherwise, you'll have runtime exceptions, and you won't be able to actually even deploy the function. It'll try to connect consumer producer to these topics if they exist, and it will fail because it's a wrong schema type. So just outlining this here, but again, this is very simple to do. No SDK required to do a simple Java native function. Python is even easier. You just define a single method called process as shown below. And you can just do, again, you do some implementation to it. You do return, everything else is the same. The method that gets passed in, the data that gets passed in is a message from the configured input topic, and the return step method publishes a string to the defined output topic. But we quickly realized that both those APIs had some limitations. They had some different capabilities, things we wanted to add to the framework that weren't there. So we decided to quickly develop an SDK, software development kit, for Pulsar Functions, and added support for Go programming language as well. So in addition to Java and Python, you can now write language functions using the Golang library. It gives you a much richer API for more complex use cases for multiple outputs. You saw previously, you can return a single, publish to a single topic. With Pulsar Functions SDK, you can publish to one or more output topics. You can do things like content-based routing, right? For example, the message contains this, publish it to topic A. If it contains this message, publish it to topic B, or publish a topic to both A and B. All these different options. We added the concept of stateful functions were added as well, so you can store data internally inside Apache BookKeeper related for each individual Pulsar function. To have keep metadata in between operations. You can do gets and puts and things like that to store data to make them more stateful. Where the previous, as you saw in the previous example, the native ones were stateless. An event comes in, you publish it. You react to it, you do whatever you need to, and then you're done. You have no concept of what came before. You can't compute a moving average. Here's my average up to this point, or here's what I know about this data up to this point. It's all lost. There's no state retained. And then obviously producing the many different topics simultaneously is just one of many. The metrics thing is APIs added to the SDK. Lots of different APIs with this as well. So when you're developing with the SDK, you do have to implement a different API, a different function interface defined as part of the Pulsar Function API library. So you obviously have this dependency You bring in a context object, which is one of the big differentiations between the two, which allows a lot of these capabilities that we talked about, publish into multiple topics, statefulness, all or access through the context object itself. And it has a different method signature. So rather than apply, as you saw in the Java util function definition, this one has a process definition as well. Again, it's also strongly typed as an input and output type. And the second parameter is the functions API context object, right? So this is showing the exact same method we saw the native one, but as a Pulsar SDK enabled function here. So again, not doing much with it at this point, but just showing it's a different API, different implementation in this particular slide. Now the process method here, this is more about the API here, and this is sort of showing it out that it has, again, this is the single process method. It's strongly typed, so you specify the output type, the return type, you specify the input type. These match the schemas, again, of the respective source topics and target topics, respectively. Again, it takes a context object and it can throw any type of exception as well. So again, this allows you to, takes an incoming message and returns a new message or a completable future. And you can use the context object to send it to different topics as well. And again, you have access to a state store API. Oops. Now for the Python, there's a Python version of the SDK as well. It looks something like this. You need to obviously add the Pulsar client dependency to your Python installation first. Then you can import the function method from the Pulsar library as shown here. You create your definition class here for your function that implements function. And again, it takes a process method defined here, taking itself, the input type, and the context object as well. This is again showing just a simple processing here in the way that you set up a Python enabled SDK Pulsar function, just the method definition. This is your basic framework. I think I have to see if the chat GPT can generate these automatically. I know it can do Java ones. You say, create me a Pulsar function that does this. It knows how to create this, the boilerplate code for the Java ones. I have to see if it knows one for the Python as well, but it's basically a very boilerplate process for that. Last but not least is obviously if you want to write your Pulsar functions in Go, this is how you implement the SDK as well. You have to implement the Pulsar function Go library as shown here. The input statements, you define the handle requests method that takes in, again, the context object. This because of Go, they're inverted. Context object comes first, and then your input type, whatever your schema type may be. In this case, we just did a byte array, showing that you can throw an exception by saying there's an error. Then you do some processing on it, and that's it. And then you wrap it in a main function and say start handle request, and then that's it. It starts a function. It registers, it creates the producers and consumers, and just executes this code every time a new method comes in. So this is basically how you do a Pulsar function SDK in Go. So that was up till 2.10, right? That's Pulsar Functions SDK. And then the 2.10 release, we added an extended SDK library that provides 2 additional methods, allow you to initialize and release external sources. So the initialize method is called once when you first start the function. You can do any sort of initialization code done there. Previously, you had to sort of handle this with logic yourself to check to make, have an internal flag like initialize, run some code. Otherwise, this gets done, but now allows you a simple place to do things like connect to a database or connect to a cache or do some library initialization, whatever sort of static objects, singletons you need to create. You can be done the initialize method. And then somewhere there's a close method that gets called right before the function is shut down and terminated. It allows you to close any sort of open file handles you have, database connections, things like that, and turn all these things down easily as well. They look something like this. This is the API we've added. So initialize takes a context object. And a good approach is obviously inside the context. I don't know if we show the entire API here, but there's several methods in the context object. And one of many is you can get a user configuration map. So you can pass in dynamically configurable user properties in a config map, a key value map to get this information back. And then you can take that information and get those different values as you want from that map, the connection info, to get that information, pass it in for your client initialization, lookups, whatever you want. You can pass in whatever values you want here and use them to initialize, connect to different properties, in this case, a Redis client. The process method is as it was before. Nothing's really changed. That signature is exactly the same. This particular case, you're using the client object because you assumed it was always used. I guess this should really say Redis client, but that's fine. Basically, you get the concept that we've initialized it first, and now we can use it to do accessing. So this is basically going to this method is going to take the input as a key to do a lookup into your map and then return the associated value from that input, your client cache, for whatever reason. And then finally, the close method allows you to do the closing of the client itself as well. So this is basically one usage pattern for the extended SDK Pulsar function. So after you've written the code, so giving you an outline of what the API is and how you're going to write these individual functions, and you can think of a lot of different things to do. There's lots of examples available. Again, you can go to the GitHub Pulsar library and get some example functions from some more realistic examples. But once you have this code in place, obviously you have to package it in such a way that it's can be deployed to Pulsar cluster and be executed inside the serverless framework of Pulsar Functions itself. So let's get into how you package each one of these artifacts using the different programming languages, because it varies based on the programming language that you've written the function in, obviously, right? So the supported deployment formats for the Pulsar functions, obviously vary based on the programming language, as I mentioned. So for Java, you can either use an Uber jar file or a nar file. Both of these have to contain all of these have to contain any third-party libraries you include in your code. There's no limitation on that inside as far as Pulsar functions are concerned. Just because we've shown simple blocks of code in the previous examples, does not mean they have to be that. They are full functioning client libraries. You can include any sort of third-party libraries you want, things to do machine learning, things to do sentiment analysis, things to do database lookups, all these different libraries. And all those have to be included in these artifacts. Don't assume anything's going to be available at the function runtime library. For Python, you can use either a single Python file, a zip file, or if you're going to run in the Kubernetes runtime environment, pip install is also an option. You can have the Pulsar function library spin up the runtime of Python itself, and then basically interrogate the content itself to use pip install to do use the Python package library manager called pip to do an installation of these dependencies for you as well. That's another option. For Go-based functions, they have to be compiled and packaged as a .go file. That's really the only way to execute any sort of Go code, and Pulsar functions are not any different. They're the only compiled of the three languages supported. So if you want to do a jar file using for your Java-based Pulsar function, then the easiest way to do that is to use the Maven assembly plugin inside your POM file, and be sure to specify the class, the full name of the function as the main class of your generated jar file. So it's going to, at runtime, make sure that that's the class that gets instantiated and executed. If you don't do that or you skip that, then it won't work. If your Pulsar function uses third-party libraries, as I mentioned earlier, be sure to add this jar with dependencies description reference inside your Maven assembly plugin to guarantee that it's going to go out and grab all of these individual third-party dependencies and all their dependencies, do a full static analysis, pull in all the dependencies, bundle them in a single jar file, and all of that is highlighted here in this link here. You can go to this link to see additional details about that, but this is basically the steps required to make sure that those are the two key components. Make sure your main class is specified and you include all the dependencies, otherwise it will not work when you go to run these functions. Now, if you're using a Maven to build your Java function, you want to package it as a nar file, then you just need to use this specific NiFi nar Maven plugin, and automatically handles the bundling of all the third-party jars for you automatically. So it does what all the Uber jarring does. in a much simpler interface. This makes it easier than the previous step. You don't have to specify the main class. You don't have to do the jar with dependencies. It bundles all that information for you as well. If you want to take this approach, here's a link to the documentation for greater details on that, but it makes it very easy to do. There's examples out on the internet that do both. That's really a matter of opinion or preference over which one you use. They're both going to work either way. To package Python functions into a one-time Python file, you need to do these three steps highlighted here. As we mentioned before, you have to write the class as we saw before. It inherits from a function, has a process method as well, has that defined there, has install the Python client, and then copy the Python file to the Python broker so you can deploy it from there. So you basically, again, this was one that has no dependencies. This is a simple self-contained Python library here. This is all you need to do. The details are defined here. This is more simple approach. If your Python library does not include any third-party dependencies, you can get by just deploying it as a Python file and nothing more. And that's simple to do. See the packaging details at this link. So this is just an example. Again, you import Pulsar function. This is just, again, you're defining to extend the function. You have an initialized class, and you have the definition. This is an example of something you can deploy as a Python file only because there are no other import statements here other than from Pulsar. And so when you at the Pulsar function runtime, this is going to be available. So that's fine. Everything else is self-contained. So this is just an example of what you can deploy as a Python file. To package a Python file with pip, using the pip installer, then you have to do these particular steps instead. Here, again, this only applies if you're deploying it as a Kubernetes pod. We haven't talked about runtime environments yet, but this is one of the preferred options is Kubernetes pod. The other is a process. If you're running it as a process in a function worker, this is not an option because we won't do this stuff for you. But if you're running it as a Kubernetes pod, then we can do this additional installation, right? So the first thing you need to do is add the following in your function workers file. Here, you need to add this particular, set this to true. This is defaults to false. Basically, it's a flag that inside your function worker, which is a separate runtime environment that runs the actual Pulsar functions. It's a configuration set to false. It's saying, I will not let you change any user code. We set that to true. Then you use the generate sh script that is already provided in your in this particular directory of your Pulsar functions or inside your Pulsar distribution. So if you download the Pulsar library, you look at the Pulsar functions path, there's a script Python directory, there's a generate.sh script there that you can use. And that will generate a wheel file for you in the specified, whatever you specify the output directory to be. So here's an example of, again, if you're in that particular directory, you say generate sh, you give it the full path name to where your Python function is, and you specify where your output directory to be, and then you specify a version as well. Like I want this to be version 1.0.0 of my particular function, and it's going to generate a wheel file for you. Now, wheel file in Python basically is a manifest that contains not only your particular but your function, but all the different dependencies that it has, and then that wheel file itself is what's used internally to do the pip install for you automatically, right? So once you make that deployment, you have that particular wheel file, you do a deploy on that, and then the function worker, because it's configured to install the code dependencies, will access that wheel file and say, I need to install this, I need to import that, I need to import the other thing, and it will run through the process of doing a pip install for each of those dependencies and make sure they're available in your runtime environment for you automatically. Go is by far the easiest one. Again, you just write your Go function. As we showed in the API, you have your simple definition of handle request. You have the context object, you have your input type, you have your main method that calls that basically, and then you take that information along with any dependencies you have and use the Go build tool to build your Go file name here. It's going to produce an executable Go artifact. So you just say Go build whatever your function name is .go. It's going to return a configurable artifact file, and then you just can deploy that. So let's talk about, so once we've either generated a jar file or a nar file or a wheel file or executable Go file, whatever we have, now we have them all packaged. Now we need to actually, submit these to Pulsar so they can be deployed and run. And then we'll talk about the command line and how to do that. And then we'll get into some of the details about how I configure my Pulsar functions, right? Because they're simple, they create the producers and consumers for you, but you might want to change some of those configurations that are available to you through the regular Pulsar client API, right? You want to specify different a subscription type, or your schema type, or your user config properties, or things like that, what your log topic is, things like that, your input topics, all those different ones have to be configured as well. And we'll show you how to do that as well. So after you've packaged your Pulsar function into a deployable artifact, you can use, there's a Pulsar Admin CLI tool that allows you, this is the basic way to deploy your functions, and you can deploy them in either cluster mode or local run mode. Now, cluster mode is what you do in production. You submit it up to the Pulsar function cluster, and the cluster hosts that particular Pulsar function, the execution runtime, and he's in the Pulsar cluster is responsible for making sure it stays running. However many parallel instances you have are running. If it dies, it automatically is supposed to restart it. All those different things. All the code executes up in your cloud instance, wherever your Pulsar cluster is running. Local run mode is used for debugging. Basically, you're saying, I want to run my Pulsar function locally on my desktop machine, but I'm going to still connect to my external Pulsar cluster running somewhere else, right? So it's going to configure, it will still consume messages from your Pulsar cluster in the cloud, but the execution of the Pulsar function code itself is on your local machine. This allows you to set breakpoints and things like that, do debugging, lower level testing, things like that. So there's two options available for your deployment mode inside Pulsar functions. So again, if you want to start a Pulsar function in a standalone environment, you can do this using local run, excuse me, and then you have all these various configuration switches, right? So this is the very basic way of doing it. You're going to, again, Pulsar admin functions is the command, local run is the sub command. You have to specify where your artifact is and give it the fully qualified name. For Java, it's obviously .jar. For Python, it's --py, and for Go, it's --go. So that tells us which artifact it is. You have to give it the class name, fully qualified class name of the main class, the function to execute, so it knows what class to instantiate internally, and spin up and run. Inputs is the name of your one or more input topics. You can specify this is the source topic from which I'm going to get messages arrive inside the Pulsar function that the code then gets executed on. And if you specify a return type for your Pulsar function, again, which is optional, you can define it as void. If you don't want to have a return type, you just want to process the messages and not produce any output. That's an option. But if you do specify return type, then you specify your output topic here, and you can only have one output topic, but again, you can have many input topics. And then last but not least, you have to give it a name for management. This is how we store it, catalog it inside Pulsar itself. And this is where we associate state with it. This is where we associate the version and the artifact interface, and that's all defined here. So this is your bare minimum set of requirements. All your default configurations then for your producers and consumers apply. You can look at the documentation for those defaults are, but this is your bare minimum for that. For Python, again, if you created a zip file, for example, then you use a similar command. You do -py, as I mentioned before, pass in the artifact with a zip that contains all of your third-party libraries. And this is showing you a different way, which we're transitioning to the preferred way, which is a configuration file. So best practice is going to be not to have to memorize all these different values and configurations on the command line every time and execute it. You can store that information in a YAML file and associate it with your function so that you can configure this thing and have a lot more control over what sort of properties you want to set. It becomes an artifact in its own right, like your function artifact itself or your class. They should be managed together so you can make changes to one or the other. This is basically saying read this YAML file, and all of my configuration information is in there at this point. And this is a best practice. So this is what I'll show going forward. I won't use the command line switches. So the nice segue is this configuration file is used to configure functions. So let's talk about how we configure functions and what some of the different options you have when configuring Pulsar functions. So you can basically break these these configuration options you have down into different categories as shown here. The minimum are obviously the required set of properties that you need. Again, you're going to need the functions fully qualified name, the deployment artifact, what's the name of the artifact that contains the source code you're trying to execute, and also it specifies runtime environment. Again, if you're doing --jar, we know that it's a Java function. Doing -py, we know it's a Python function, etc. Obviously, your input, output topics, things like that. These are the bare minimum things that are required as well. Optionally, again, if you're doing any sort of encryption or decryption messages, you can specify those in their own category. You can further control your consumers and producers with the schema types, and you have specialized serializers, deserializer classes defined, other properties around, so again, such as the various subscription types and policies and names, auto acknowledgements, things like that, producer configurations as well. You can, everything basically it's available in your client API are available here. You can pass them through to create these producers and consumers that are created for you automatically under the covers. There's some resource allocation. Again, these are only honored if you're deploying to Kubernetes. So you can say, I need, this many CPUs. I need, when I'm creating my pod to run this function in, I need this many CPUs. I need this much RAM. I need this much disk, if that's something you want as well. And then when it deploys the pod, it goes out to the scheduler, grabs those resources, and makes sure those resources are allocated to the pod running the Pulsar function. And then, as I mentioned before, you can pass in that user config map. We showed in one of those examples in the extended SDK version that there's a way to pass in key value pairs. So if you want to have variable substitution inside your Pulsar functions, then that's a way to pass in however many environment variables you want as well. Lots of different categories on that. And again, there's documentation available in the Pulsar docs around creating these different configuration values. So here's a simple example of a function configuration YAML file. So again, when we're configuring, we say -- my function configuration file or function config file. This is what this content has to look like. You specify the tenant and namespace that the function is going to be running in. Whatever the name of your fully qualified name has to be here. Your input topics, again, this is just showing an example. You can specify them as a list. I can listen to more than one input topic, and this is shown here. This is how you define an array in YAML. Output can only be a single option. Here we're specifying it's a jar file, so again, you can give it the fully qualified name to the jar. Parallelism, how many instances I want running. Resources here. Auto acknowledgement. Do I want to, every time I get a message, and process the message in Pulsar function, you can say I want to automatically acknowledge it versus having to explicitly acknowledge it in the code. And then you can use a user configuration key value map. So just passing key values here. So this is a very simple example of this later. So let's talk about the Pulsar function runtimes. So we mentioned earlier, right, there's different deployment options for Pulsar function. We saw cluster mode and we saw local run. But in cluster mode itself, there are different options as far as where these Pulsar function instances can run. So we'll talk about function instances versus function workers and some of the different runtime options that are available for Pulsar functions. I've alluded to the Kubernetes, and we'll also talk about some of the other ones here as well. But a Pulsar function instance is what's created when you do that create command we saw from the CLI. So you create your artifact, you have your jar file, you say Pulsar functions create, and you give it, the configuration file and your artifact, give it a name like that, and it's going to deploy that information up. It uploads that artifact to Pulsar, and then under the covers, it creates all these different elements executing inside the runtime environment, right? So a collection of consumers one consumer per input topics you specified. So in the previous example where we had two, there'd be two separate consumers running and configured on each one of those input topics. There's an executor framework that wraps it, again, based on the programming language of your artifact, to make sure that the function gets invoked. And there's a runtime environment for it. And then there's optionally a producer, again, that sends the result of the function to an output topic. This is all the boilerplate code that's created for you automatically and runs inside what we consider a Pulsar function instance. Every instance has all of these things in it. A Pulsar function can have multiple instances. That was the parallelism definition of that. So if you say parallelism of 3 there for an individual function, then there will be 3 separate instances of that, each with their own consumers and producers and execution framework for that, right? So it's not multi-threaded at that level. It's really run as individual instances as well. So this is conceptually sort of how it looks. There's a function instance running here. So you have input topics coming in. There's a consumer dedicated to each input topic that you have specified as the inputs for the function, and they trigger and execute so they'll consume the message, they'll get the message, and then they invoke the code. They will call the process method on your function class and pass in the input message as that input parameter, right? So they pass that in. They also pass in the context, right? So they actually invoke that method here, and that's done in the executor. And again, there's an optional producer method that if the return from that particular function, if there's a return value, it gets passed to the producer, and the producer then produces a message to an output topic. It has a connector to a log topic, as I mentioned before, and it has direct access to Apache BookKeeper, so you can do stateful processing, get state and put state, and all these different options that are available for you are accessed through the function instance. So this is what a function instance is: consumers, producers, and a runtime framework for the Pulsar function source code. Now, function workers are individual components, separate pods running inside Pulsar function itself. They're associated with it to Pulsar. So you have, by default, you have your broker components, right? That's your stateless serving layer. You have Apache BookKeeper bookies. That's your persistent storage layer. You optionally have Pulsar proxies. And this fourth option here is what's called function workers. And they're designed explicitly for the running and executing individual Pulsar function instances, right? So within these function workers, each function can be executed as either a thread or a process, depending on the selected function runtime environment that's been specified in the function worker.yaml file that we talked about earlier, where you can say, I want a pip installation or things like that. Each function worker is configurable. You can specify the runtime environment there. Alternatively, if you have a Kubernetes cluster, then the functions can be spawned as stateful sets, individual pods within Kubernetes instead of running inside function workers. So there's different options as far as deployment runtimes: threads, processes, or Kubernetes pods. So again, this is showing you each individual Pulsar function worker and what exists inside of there. So again, it's a logical component that monitors and orchestrates and executes an individual function in a cluster mode deployment for Pulsar functions. The function workers, and there could be many, form a cluster. There could be a cluster of these worker nodes. And the workflow is kind of shown here. So we've highlighted here. So the user interacts with the REST server using the Pulsar Admin CLI and says, hey, I want to execute a function instance, create function. That's what we saw in the deploying section, right? You have your artifact, you say deploy it, you specify your config file, and you give it the artifact, and you call the REST server with that. The REST server responds to the request and takes that information, says, okay, I got it, and passes this information onto the function metadata manager. And this metadata manager writes the request and updates the function metadata to the topic. So this, again, we store all this information. This is your configuration information. That's why it has to be uniquely identified as a tenant and namespace. Each function is associated with that because this is stored by name. It creates a fully qualified name for each function. We put it in this topic, and that's its configuration. That's stored there. Once it's persisted, it returns back. And the Pulsar manager reads those updates. Next, the scheduler comes along and says, okay, I have a Pulsar function. It's supposed to be running. It's going to write the assignment updates. It's going to basically figure out where to assign this function to run. It looks at this Pulsar function pool. It does some scheduling, says, okay, I got to figure out where I'm going to run this Pulsar function instance based on its resource requirements. So that's what the scheduler manager does. Once it picks a function worker to run the function instance or instances, it's called an assignment, and it writes that assignment to an assignment topic to track where these functions are running. So it says, okay, I'm going to run it here, allocates resources basically. And then the function runtime manager listens to this topic and reads this assignment update. So we'll get a message that says, okay, there's an update. I've added a new function worker. I've deleted it, something like that. Again, you can do a delete, comes through here, and you delete a topic and it gets removed from the assignment. So either way, it's either I'm adding it, I'm scaling up the number of instances, or I'm creating a new one from start. This function runtime manager gets these updates, keeps an internal state of all this information, and then it's responsible for basically materializing the new assignment and starting or stopping the execution of the function instances. So it takes the request to assignment and makes it reality. It creates the function instances, instantiates them at this point, based on which function workers that have been assigned to it, spins up the runtime environment, right? And that's it. Then everything up and running, everything goes well. Then the membership manager, it's the last part of this particular sequence, requests the coordination topic to elect the lead worker, and all the workers subscribe to the coordination topic. And the active worker becomes the lead and performs the assignment, guaranteeing only one active consumer for this particular topic at any point in time. So again, there's a coordination mechanism done there to make sure that everything that reads updates from the coordination topic to make sure that that if, for example, a function instance dies, it has to be run somewhere else, this coordination is handled here. And this membership manager tracks the lifetime of it after it's been set up and run and assigned somewhere. The membership manager is responsible for running the rest of all the function instance runtime environment, keeping them up and running. And again, and here the function instances are deployed across multiple function workers. So this is the entire execution framework, and shows you the difference between the Pulsar function workers, which is the coordination and the scheduling system for Pulsar functions running in these individual nodes called Pulsar function workers, and the function instances just get deployed across all of those. So again, as I mentioned, Pulsar function instances are invoked inside a runtime, and any number of these can be running in parallel. So just to summarize again, there's a different trade-offs between each one of these. So, thread mode is one. It can run inside the same JVM as the function worker. Again, this is not recommended for production. This is also available in brokers. We used to be able to run it in brokers. I don't think that's supported anymore. Another option is if you want to run them as processes. Each function runs as a separate process on the function worker machines themselves, and multiple function workers scale out across. So each instance would be its own process. So I have 5 parallel instances of the same function. Each would be its own process running there as well. And as we mentioned before, Kubernetes function runs as a pod on the Kubernetes cluster. It's wrapped in a stateful set to say, I want one instance of this running. So this automatically handles failures. If the function instance were to crash, Kubernetes takes care of making sure that it gets a pod gets recreated and started for that. It also allows you for easily scaling out. And the function worker coordinates with Kubernetes to do the assignment on that particular process as well. So let's walk through the function deployment lifecycle steps when you do a deployment, right? So as I mentioned already, you can either run a separate cluster, just access Pulsar, or they can run in the same process as the broker. Both have a lot of utility mentioned here. So again, the function worker can run either as function workers or inside the same broker as a thread. These are your different options. So a function gets created on a function worker and is initialized. Then the function API starts a consumer, or consumers on the topic, and starts feeding the function. Again, it creates a consumer. It calls that execute, calls the process method on every time a new message comes in, passing in that individual message. It also starts up a producer API if one's defined as an output topic. And then every time a return value, again, if the Pulsar function method does a return, then all these values are captured and published automatically to the output topic as well. And that could be on a different broker. This is just showing you I could be consuming from this broker and publishing to this broker as well. So last but not least is then obviously the function mesh. So we saw in the previous example, it's that this process has to be done to deploy. It has to be done individually, every individual function one at a time. That becomes a bit cumbersome. Doesn't scale well as you start adding the number of Pulsar functions used for your solution, right? If you have one or two, it's pretty easy to set that up and running and keep the configs and have a script that starts them up and runs them. When you start to get into 10s and 20s and 30s, then it becomes a little more harder to maintain, particularly if you want to use your Pulsar functions, as we mentioned in the first section, as a change sequence of events, like an ETL pipeline. I want to do function 1 has to run, then function 2, and then function 3. And I want them all to be treated logically. They'll have to work together. It doesn't make sense to have one without the other. And so that's what FunctionMesh was designed to do, to make bundling and grouping of these Pulsar functions much more manageable, treat them as a logical mesh of like an application unto itself as a sequence of smaller Pulsar functions. So conceptually, the definition or the language to use inside of FunctionMesh are streams, functions, and connectors. They each serve a different purpose. Obviously, the stream is your maps back to your topic. It's a append-only sequence of events, of facts. A function is your lightweight event processing that consumes the messages, does some processing on it, and produces to one or more output topics, or actually, output streams. And so it could be a just logic stream mutator from one stream to another. And then obviously the third definition is connectors. It's an event processor that either brings data into a stream or publishes data from a stream into an external system. And there's two types supported in Pulsar functions. They're basically mapped back to the Pulsar IO framework, which are sources and sinks. So basically FunctionMesh will support Pulsar IO connectors that are of type source or sink as well. So what is a function mesh? It is just a collection of function and connectors that are connected by streams that are all orchestrated together. So you can think of it as a large DAG or directed, acyclic graph, although I guess cycles are technically could exist in them, but it doesn't really make that much sense to have a cyclical graph in there. You can think of it as just a mesh of data comes in from this particular source, goes to this input topic or stream. There's a function that processes it, writes it to another stream, another function that consumes it from there, and then eventually writes it to a source and pushes it back out, for example, right? So they all share the same life cycle. They're all managed collectively as one larger unit. You do not have to, if you have 5 functions all that need to be orchestrated together, you don't have to have 5 separate create commands, stop commands, update commands. To do that, you can define them as a single logical unit, and they all either get started together and stop together. And this makes it much easier to manage them. There's all the functions are started when a mesh is created and terminated when it's destroyed. And the functions and connectors in the mesh are auto-scaled to adjust to the workload. So they detect back pressure between the two. So if it's falling behind on an input topic or the stream is getting further behind, we can automatically detect that and scale up those number of instances, assuming that subscription types supports it. If you have an exclusive type, then there's really not much you can do. If you have a shared subscription type, then you can obviously scale up those. And again, logically, you can think of it as a graph, as kind of shown here, right? So you can have one or more input sources coming in, and then those input sources write to a stream, and these functions, you have different functions consuming off of that same input topic, doing different things, doing some enrichment, doing some transformations, things like that, eventually publishing that data back to an output topic, having a sync, so going to Elasticsearch finally. And this is just one way logically to think of it. This is just one example. You can have multiple functions. You don't have to have sources. You don't have to have sinks. You can have all functions. You can have sources and just sinks, whatever you want. Any combination of these are all supported. But it's just basically saying all of these different units, these 5 blue boxes are all separate individual pieces of code, user written functions here for 1, 2, and 3, a Pulsar IO source connector, Pulsar IO sync connector, maybe from Connector Hub, all wired together, all to do one particular piece of logic. Think of it logically breaking it up into individual methods that process the data from the database and enrich it, transform it, put it into Elasticsearch. Under the covers, what FunctionMesh is it's just a Kubernetes operator that enables users to run functions and connectors natively on Kubernetes. So again, it only applies to this feature is only available for the Kubernetes runtime. It's not available for the process runtime, not available for the thread runtime, right? So this is because it relies heavily on Kubernetes scheduling functioning and make sure that everything's up and running. The serverless framework also, coordinates these different functions and IO connectors together to package and deploy more complex streaming jobs as a single logical unit. So how it works, again, it leverages the Kubernetes APIs, so it can be managed using existing Kubernetes tools. We didn't have to write a separate API for that. So instead of using the Pulsar Admin CLI tool to do the function admin, things like create the tool, or create a function, update a function, delete a function, you can now use the CubeControl to submit a FunctionMesh CRD manifest, which is just the custom resource definition. So you can define, hey, it's a way Kubernetes defines resources. Those of you not familiar with Kubernetes, I definitely encourage you to do some research on what a CRD is, but it's basically a text file that Kubernetes can process to say, these are my different resources I want to run and execute, and then you can embed functions inside of there. And then that way the CubeControl looks at it and reads it and says, okay, this is what I have to do. It translates that CRD manifest into the corresponding admin requests as lower level REST APIs we saw in the function workers to create Pulsar functions, to get them scheduled in the Kubernetes runtime and then get executed as well. Again, so if there's any change to the CRD, so you can have an existing you start with the CRD, which we'll see examples here in the next slides. It uses that to create the Kubernetes resources and run the defined functions inside of that, right? So you can sort of internally, this is what it looks like. You're going to have different function YAMLs and source YAMLs and syncs, and your function mesh. All these configurations get processed by the CubeControl tool. They interact directly with the Kubernetes API. It translates that into different functions, and so the FunctionMesh operator has a corresponding CRD custom resource definition for each one of these there inside your individual mesh. It updates those, so it can say, I want to change this. You do an update, it updates the CRD, and then these CRDs get translated into stateful sets with individual pods for each individual function. So this is just expanding one. There's multiple functions, but inside a pod can be a function, a source, or a sink. Each one is sped up and running independently. They're auto-wired again from the input and output topics for you as well. And then these function runtimes can interact with the Pulsar cluster. So they could run inside the same Kubernetes cluster, typically within the Pulsar namespace as well. So the networking connection is minimal. They go straight, they're within that same subnetwork, so they can connect to one another and access the data. So the function runners can create their consumers to this Pulsar cluster, consumers and producers, and it's all inside that individual pod as well. So it's all runs there, and this is what the FunctionMesh internals look like. So if you want to use FunctionMesh, you think it's the coolest thing, basically you still need to package your functions as you did before. So you still have the artifacts, you still create these jar files, Python files, pip files, Go files, whatever you want. You can mix and match them too. There's no reason you can have to have all Python or all Java. You can mix and match them, but then you define your CRD custom resource definitions for functions and connectors and FunctionMesh, and then submit them to the Kubernetes clusters. Using the CubeControl apply, you just say, hey, this is my CRD for this particular resource there, and then it knows how to read it. The FunctionMesh operator was able to read those CRDs and convert those into the actual REST calls and Pulsar functions to create and define these artifacts as well. Right. So once the Kubernetes receives the CRD, the FunctionMesh operator, there's listening and schedules these individual parts and runs the functions as a stateful set from there. So you can say, this is my function as well, define them all together. So if you want to define them in a single two functions rather than one. So we saw in the previous configuration file, we saw when we were configuring the Pulsar functions, you had one config file per function here, you can have many, right? So this is just showing you 2, but 2 is just an arbitrary number. You can have 5, you can have 10, you can have however many you want. And it's just defined here, right? So there's a special type called a FunctionMesh when you define your particular CRD. This is your API version, the type, the metadata, any sort of metadata you want to add. That's up to you for tagging, things like that. And then here's the real meat of it. The specification, you can specify as many functions as you want, each with a different name, class name, replicas, as far as instances. And then the configuration under this point is exactly the same as you saw in your config, right? So this is my input topics. Now this is the schema type for this particular input topic. This is the output topic that I want. For Pulsar, this is my Pulsar configuration. This is my jar file. This is where the jar file is located. Similar, you can have another function here, a second one here having its own definitions, replicas, input topics as well, configurations, and so on. And so this is one larger manageable unit. You have to change 1 or 2 things. Instead of having separate ones managed, you can have it all in a single function, and then you do a CRD CubeControl deploy, and it just executes, and all of those individual functions defined here in the CRD are inside this definition file here are just spun up and for you automatically. You do a create, they get spun up. You do a delete, they all get spun down simultaneously at the same time. And that's all I have.